Welcome. Let me say something about the odd perfect number problem because it appeared in a recent Scientific American article. It's a beautiful problem, undervalued. It did not make it into the problems of Hilbert. It did not make it into the millennium problems. And there are really kind of some problems which should have been replaced, like young Mills, even so a mathematical physicist. This is a scandal problem. It is not well defined what you actually mean with the problem. It needs a judge or a VIP mathematician deciding, oh, this is a solution. Also here, the axioms of physics. What the hell do you mean with the axioms of physics? So it would have been nice if Hilbert would have taken, instead of such a nonsense problem, taken a concrete problem which is really beautiful and has culture and has history, and some of the best mathematicians have worked on this problem. So there are three outcomes. Either there is an odd perfect number and you can find it, or there is none and you can prove that it doesn't exist. And then there is the third possibility, like always, you actually there are no odd perfect numbers, but you cannot prove it. So that's always possible. You know that the axiom systems are just not strong enough, and you would have to take this as an axiom, like the continuum hypothesis, which had been also one of the Hilbert's problems. So there are lots of guidelines what you actually should believe, and all these guidelines here in mathematics, they are not rigorous, and you can actually not prove any of this. Like Occam's razor, you cannot prove that the simplest solution is the best solution. It's not true in general, or that the law of small numbers, especially the strong law of small numbers, there are many examples where the first counterexample is extremely large. Or the Church-Turing thesis, we just assume this to be true, that everything we can compute with a Turing machine. Of course, we cannot prove it. There could be some magical machine, some super quantum computer which does things, not more efficient, but can do things which we cannot do. But nobody believes this happens, or that we can think, oh, A is true and B is true, and then afterwards we can be using that A and B is true. This basic logical thinking requires that our brain works, right? That our memory works, that if you keep A in the memory and B in the memory, we don't, in the next step, lose what happens with the memory A. It's not politics where we do that, where we forget about the past. Or the consistency thesis also, we have to assume that the foundations of mathematics are true. We just take this for granted, and Gödel showed that we cannot prove this. There is no consistency proof. We cannot prove consistency within the system. You would have to go out of the system, but then you are in the same problem again. You would have to go out of the system to prove consistency. So we have never, this is something I've never seen, but I think it's a principle. Somehow I was taught this by my teachers, like Trubowitz once said, if something is, equality is true, then you actually have some symmetry. So symmetry, or so there's a reason for something to be true. Now, this principle is the reason why I believe, like Turing, that the Riemann hypothesis is false. So there are some large, places on the some large routes which are not on the axis. The real part is equal to 1/2. So nobody can, of course, this is not a principle also you can prove, but it's a guideline. If there should be a reason that it's true, then it's true, but then there is a reason for it. And the same thing is for this odd perfect number problem. We don't see any reason why it should be false. And Descartes was giving a very nice example of an almost perfect number, which kind of rules out lots of mechanisms why this should be not true. And so there's no mechanism known which prevents us from finding an odd perfect number, and that's maybe then a reason that there is an odd perfect number, even so it might be very large. So I mentioned this already in my 2007 article about kind of a talk, math circle talk for high school students about the odd perfect number, and I suggested kind of, and I was actually doing that myself, build such a machine. This is call it the odd perfect number bomb. Of course, Turing, was building this famous bomb for cracking the Enigma code, and this is one of these parts of this bomb. Had 36 wheels, and you tune these wheels, and you try to find the solution to your problem. And so what happens is these numbers, so what you take is you just take a list of primes, finite list. Here it's like 36 different primes, maybe each has 1,000 digits, or a few thousand digits, and then you have numbers here which you kind of the other exponents. So you build numbers like that. So they become large, millions and millions and millions of digits in general. And then you look at these numbers. So this tells us whether the number is efficient or abundant. So either this number is positive, or it's negative, or it's zero. If it is zero, then you have a perfect number. So if you take only odd primes here, then you are searching for odd perfect numbers. And so you want to make this zero. What actually happens is if you tune the indices, if you just tune the wheels, this changes this number very, very little. So you can hope that you can kind of use some kind of multi-dimensional Chinese remainder problem to see how many times you have to turn different wheels to get closer to zero. And then once you are closer to zero, you do it again. And so you turn the wheels again to make it smaller. So this is like a descent, like what you do in AI or what you do in mathematics in general, this gradient method. So you go and try to make this small. And what happens is, in the nature of things, when you change the ends, these numbers changes very, very little. So you still you're searching in a huge, huge, huge space. So you need definitely results. And the problem is we don't have, in multi-dimension, we don't have good sieving methods kind of to find small lattice points in a lattice. So if it would be only one thing, then you can use almost periodicity, and you can kind of tune in. You see the continued fraction algorithm, you can tune to the root pretty fast. But in multi-dimension, that's why I actually worked on multi-dimensional Chinese remainder theorem also. So we have problems where we have many variables, and we have to tune them. Each of the variables, when you tune them, are changing things in an almost periodic way, and then you need kind of some combination of reals, integer combinations of a lattice. In a lattice you have to find points which are close to a lattice point. So this is a problem which has some mathematics. There's some mathematics like LLL algorithms. There are some tools to do that, but nobody has kind of found this. So my guess is, and that's what I kind of was cited, is I guess is that in the next 100 years somebody will build such a machine and actually find odd perfect number. It might be just billions and billions or billions of digits. That's it.